for that case, we came to a familiar-looking but easily confused result, right, which was that the potential energy for two charges was K, Q1, Q2 over R. Okay, where R is a different, and the part that gets confused there is very similar over here, except it's an R squared. Of course, this was magnitude of the force. This, of course, is potential, so there's no vector here, right? But it also means that you just calculated all these numbers, right? We know what the R is, square root of 2 times 0.3. There's all the stuff on top. So it's actually just this number times square root of 2 times 0.3. It's pretty easy from here to get what this is. In fact, that second part is far easier than the first part because it's a scalar quantity. So 3 times 10 minus 9 plus 5 times 10 minus 9. Again, keeping everything in SI units. And then the only hard part of this was knowing the distance between these two, which was the square root of 2 times 0.3 meters. Again, keeping everything in SI. That would give me out a answer in joules. And I wouldn't, I'm not going to require that in these things where you're trying to keep track of the units of dielectric, constant or K, that you write them out explicitly. But as long as you stick with SI, you'll be all right. If you start putting in millimeters or some other units, then there could be a trouble. And in this case, this was about 4.5. That's 10 to the 7 joules. That was actually much easier than the first part. But this wasn't a hard problem. It was just Coulomb's law, knowing direction. The last one is the harder one for sure. So it says a very thin conducting sheet is lying in the XY plane. So it's another conducting sheet problem. The reason I like conducting sheets is the fields are uniform. The current densities are uniform. They're easy to apply Gauss's law to. You take away some of the nastier parts, but they're not simple. So it says for Z less than zero, for Z less than 0, electric field is basically 50 volts per meter in the Z direction. For Z greater than 0, the electric field is minus 60 volts per meter in the. Well, this is the kind of stuff you can read, and it's like what's going on here? You got to draw a picture. You got to draw something that shows you which way the fields are pointing where. Unless you've really got good, 3D visual perception in your head, you can carry all these vectors around. You need a sketch. And so this is a charged plane, a charged surface, conducting surface with charges on it. They said was in the XY plane. Right? So that's some kind of sheet. You've got to make these sketches. It's a given that if you don't draw these things out, you're never going to get it. No way. So here's like X's and Y's are here. Z is going up like that. And which way is the field going? Well, for Z less than 0, the electric field points up. So down here, I've got E going upward. And what did I say? It said 50 volts per meter K hat. Put it right on your picture. Didn't ask for a picture, but you definitely need one. And on the upper part, which way is the field going? For Z greater than 0, it's going down. Right? So up here, Z is confusingly going down. And it's not the same strength. I gave us minus 60 volts per meter, and that's again K hat. And so one thing that threw people for sure when they counted this was, whoa, why are these fields different? I don't like that. I only know the case where the fields are the same, maybe. Anyway, all kinds of trouble. All right, so let's get to the first question. What's the total charge per unit area on the conducting sheet? All right, so how do you find that? What's the big concept that you need to grab a hold of or you're lost? How many laws are there that you have in this section? 2 laws. Coulomb's law. Not Coulomb's law, right? We're not asking for force. What's the other law? Gauss's law. You got to grab Gauss's law. And Gauss's law tells you that if you were to draw a surface around this thing and grab, some of this plate, and trying to draw like a cylinder or something, if you draw a cube if you want, it tells you actually for any surface that you draw, the integral of the electric field, which conveniently I gave you everywhere, above and below, dotted with these very area element, is equal to the charge inside divided by epsilon naught. And you notice I'm asking you about the charge per unit, total charge per unit area on the sheet. And if I wrap this, Gaussian surface, in this case a cylinder or cube, and grab some of this plane, I'm going to enclose some charge in a certain area. All right, so now all you got to do is figure out, what's the heck's going on this left side. That's E dot dA. We know which way E is pointing. E points in. So we don't have to worry anything about these sides of the cylinder because E is parallel to them. The only thing that matters is what? Upper and the lower surface, because that's the place where E is pointing straight in here and straight in there. All right, so the question is, what's that? So I can write this as, E on the top dot the area of the top. Both of those are vectors. Why? Because that was the integral. E is constant up there, right? If I integrate over this upper surface, I'm going to get E, which is always the same thing up here, times the area of the thing up there. And it's a dot product and it's a direction. And then, of course, there'll be the electric field contribution from the bottom. We'll call that E on the bottom, dotted with the area on the bottom. And that area, oddly enough, is a vector. And I'll write that as the charge inside, whatever, epsilon naught. All right, so which way is E pointing on the top? Down. Which way is the area pointing on the top?
Upward.
Up. The area pointing. Well, it's that symbol. What we mean here is that vector part is always points out of the volume, but in doubt. So the normal or the area part is pointing up. It always points from the inside of your volume to the outside. And so these are in opposite directions. So that means that when I take this dot product, it's the length of this, length of that, times the cosine of 180. So this is minus the length of the first guy, the top, times the area of the top. No vectors now. And where'd the minus sign come from? Because that was the cosine of 180. They were pointing in opposite directions. Right, and over here, what about on the bottom? E is pointing up. The normal points, the area part points down. Again, they're opposite to each other. Which means, again, this is it'd be length of this, length of that, cosine of 180. That's length of this, the length of the second guy times area bottom. Again, times a minus sign because it was a minus or cosine 180 degrees. So we got minus the length of the top times the area of the top, minus the length of the bottom vector times the area of the bottom, and that's equal to the charge over epsilon naught. Okay. So what's this length here? We'll do one more trivial step and we'll figure it out. Let me take the area of the top and the area of the bottom are the same. I'll just drive that over to the other side. I'll push the, right, so this will give you the charge over the area. That could be the area of the top or the bottom. I'll just write area of the top. And I'll assume the area of the top equals the area of the bottom. That's equal to epsilon naught times, I've got a minus magnitude of the top, and then minus magnitude of the bottom. All right, so obviously you got a minus. What's the magnitude of the top? 60, yeah, not minus 60, 60. It's the length of this vector, that's 60 volts per meter. So I'll do this part. So it's epsilon naught times minus 60 volts per meter. Why is it a minus? It's a minus because there's a minus here. And then this E top, that's 60 volts per meter. Now this next guy will be minus, what's the length of the bottom electric field? It's the length at 50. Minus 50. All right, so that's minus 100.